I don't think we have any visitors. You
David.
Yeah.
David.
Yes.
Introduce yourself.
Sorry. So my name is David, and I'm from the visiting from the Niels Bohr Institute in Copenhagen. So I'm here for a month now, and I'm working with Andrew and Zoltan from Colombia. And I have an office nearby, actually, right there too. I forget the number, but I'll be here
on this floor somewhere.
Yeah. Just this way somewhere. Yeah.
Okay.
But yeah, so I'll be here for a few weeks anyway. So hopefully I'll get to meet a lot of you.
All right. Thanks. And today we're pleased to have Patrick Breysse to talk about galaxies. Question mark. Question mark. Question mark.
All right. So today I'm going to talk about some work I've been doing here over the last few years. It's kind of a nice cap off before I leave this state of New York to become a Texan in July.
Where are you going?
I'm moving to Southern Methodist University in Dallas, Texas. And so this work was primarily done, faculty I was with Anthony Pullen and Rachel Somerville at CCA, as well as a couple of former NYU grad students, including Yucheng Zhang and Shengxi Yang. And the title I put up here is just galaxies, because it kind of expresses how I feel about them. The title I put on the internet was "A Cosmologist Tries to Understand Galaxies." And so, slight bit of background on me. I did my PhD at Johns Hopkins with Mark Kamiankowski along with Cyril. And for anyone who knows Mark, that is a very kind of pencil and paper cosmologist type of group. Mark actually had a habit of referring to all of astronomy except cosmology with the slightly derogatory term object-oriented astronomy. But over the last several years, for a variety of reasons, I have become more and more of a person who is stuck studying galaxy evolution. And so today I want to talk about why galaxies are difficult, why as a cosmologist they're kind of a pain in the neck, why they're important to try and understand, and some of the work that we've been doing to try and bring some more cosmologist-style intuition into this problem of understanding how galaxies work. And so to start off, I thought I'd give an example of what the kind of classical cosmologist-style intuition looks like. So if you were here for the Nikhil Padmanabhan's Astro Seminar a couple weeks ago, he talked about the latest data release from the Dark Energy Spectroscopic Instrument, or DESI project. So DESI is a state-of-the-art in the field of spectroscopic galaxy surveys, which is a very common tool for cosmological research these days, where you take a telescope, you point it out into space, and you measure the positions and redshifts of as many galaxies as you can. And for the purposes of the cosmology analysis, you can basically treat those galaxies as point sources. You can basically neglect all of the stuff about understanding the systems themselves, and all you're doing is you're treating them as point sources that trace the filaments and clustering of the cosmic web. And what you can do then is you can put it into what we call the lambda CDM model. That's only has two things. Cosmology has spent the last few decades in what people have called the era of precision cosmology, which is a term that's starting to lose some of its meaning for people like me who are too young to remember much of an era of imprecision cosmology. But the basic idea is you can take these galaxies, these positions, basically just a list of 3D positions, you can compute some summary statistics of those, and you can put it all into Bayes' theorem and get a posterior probability for a 6-parameter cosmological model. The exact parameters you use differ somewhat, which you call a fundamental parameter and which you call a derived parameter, but usually it looks something like the total amount of matter in the universe, the total amount of baryons in the universe, some measure of the expansion rate, which you can write down with the Hubble constant, the amplitude of the initial overdensities in the universe, something about the size distribution of those overdensities, whether the universe started with lots of large scale or lots of small scale overdensities, and a nuisance parameter that has to do with how the epoch of ionization impacts cosmic microwave background measurements. And so there's this whole history, this whole industry that has been built up several decades over taking experiments like DESI and basically doing giant Monte Carlo chain forecasts to get, big corner plots. That's not enough corners, but big corner plots over all of these parameters.
I was just simple with lambda.
So usually, in the vanilla lambda CDM model, the universe is assumed to be flat, and the dominant components are omega matter and omega lambda. So in the vanilla lambda CDM model, omega lambda is just fixed to be 1 minus omega matter. But that gets into something very important that you can then do is, because we have this very simple and straightforward model, we can easily start playing model comparison games. We can consider extensions to the lambda CDM model. And in particular, what DESI did, which has gotten a lot of attention over the last couple of weeks, is they considered an extension to this model where the equation of state of dark energy is allowed to vary. Basically, the assumption in the model is that the pressure of a fluid is some constant times its density, and for the standard model of lambda CDM, where dark energy is a cosmological constant, W equals -1, and DESI, the DESI team, basically, after fitting their original 6 parameters, they did another fit where they said, let's allow W to vary, and let's not just allow the constant to be a constant that's varying, but let's this constant vary with time. And they found, in both cases, a preference for W different than -1, and WA different than 0, at some number of sigma, like 2 to 4 sigma, depending on how you measure it.
Did they allow it to vary below -1?
I think they did, yes.
I think they did, yes. But the important point of it,
You can do it.
yeah, but for the purposes of this talk, I don't want to get too bogged down into the details of how they did this, except for 2 facts. One, all you have to do to change the fundamental physics of your model to explore some, this is a fairly important change to our understanding of the universe, that dark energy isn't a cosmological constant, it's actually something that varies, is add some more parameters to your model, rerun your Monte Carlos, and play chi-squared games. Ask if these parameters deviate from lambda CDM expectation, measure some chi-squareds, ask if the data prefer that model. The other important aspect of this
The
is that
question, what is WA?
WA, I'm probably going to write this down backwards, but the statement is that W is some constant value plus WA times 1 minus the scale factor,
I believe that's correct, yeah.
is how they do it. I always forget which way the signs go.
I believe that's correct.
Yeah,
It's like a time derivative of W.
yeah, it's a time derivative of W, basically. The other important thing about this is that in order to get these deviating constraints, they didn't just use the DESI data. The strongest constraints on this WWA model came by combining the spectroscopic galaxy survey, measurements of the cosmic microwave background, which is a 2D surface at redshift of about 1100, and a sample of supernovae in a low redshift universe. A redshift about z equals 0 to 1.5-ish, I believe. And then the DESI data themselves span redshifts something like 0.8 to 4. And so, again, the exact details of how all these things combined is something that people are going to argue about forever. Supernovae already cause a whole class of problems in Hubble constant measurements that we have heard of in some of these brown bags. So I don't My goal here is not to get into the details of this process or the incredible amount of work it takes to do at this level of precision. My goal is to point out how I can take the dynamical evolution of the entire universe, reduce it to a 6 to 8 parameter model, and then I can simultaneously fit exploding stars in the relatively local universe, the 3-dimensional positions of galaxies in the more distant universe, and some map of the map of the diffuse plasma of the extremely early universe. And I can put all of that into one nice Bayesian model. I can do priors, I can do chi-square tests, and I can get nice results out of that.
Plus nucleosynthesis.
Plus nucleosynthesis, yes, which then involves, making metallicity measurements, like measuring the line emission from specific stars to figure out the concentrations of various metals in the universe. So yeah, so if that's 4 wildly different data sets over wildly different spatial scales, different points in time, different observing frequencies, and we just kind of take it for granted that, we can put all of this together and make a bunch of ellipses and then argue about whether the ellipses touch or not. And so coming from cosmology, coming from that group in Baltimore, this is the kind of problem I'm used to dealing with. Now, galaxies don't work like that. So this is kind of a straw man example of a typical problem in large-scale cosmology. I'm gonna try to look at a kind of different straw man back of the envelope question in galaxy evolution and see how it comes out slightly differently. So all I want to know, so let's say I want to know about star formation. Star formation, you probably don't have to know a ton of astronomy to guess that star formation is pretty important to understand how things work. Say I want to know something like, I want to know how much star formation there is in the universe, and I want to know how it's distributed between galaxies. I want to know how many galaxies are there that are forming a lot of stars, how many galaxies are there that are forming very few stars, how many big galaxies are there, how many small galaxies are there.
So you also have this N that looks like an M.
That's because it has run into the arrow.
That's a problem, the NN problem.
We had this issue with Giovanni last week.
So this could be explained in a fairly straightforward way. We know that galaxies live in the most overdense regions of the dark matter, right? So we know galaxies tend to live. We have some dark matter halo with some mass m, and we tend to have star-forming galaxies in the middle of them, glossing over many, many horrible details about satellite galaxies.
Also not to scale.
Also not to scale. Nothing I'm saying in advance, nothing I draw on this board will be to scale. And so dark matter is relatively straightforward to model. Dark matter is a collisionless fluid. So we can, from, for example, n-body simulations, famously Jeremy, who I don't think is here, did a bunch of work on this. We can get a pretty good idea of how many halos there should be of a given mass. What's the number density of dark matter halos at a given mass? We have a good idea how many baryons there are in the universe, the stuff that turns into stars. And on large scales, everything is just gravity. So we know vaguely how fast baryons should fall onto a halo of a given mass. And we know from observing clouds in the Milky Way, if nothing else, what we call the star formation efficiency. We know about how quickly a given amount of gas turns into stars. And so we should be able to, at least back of the envelope level, from all of this, predict this star formation function, predict the galaxy luminosity function, predict what the star formation activity in the universe looks like. And there are various levels of complexity of this. Usually this takes the form of like a luminosity function, of like ultraviolet or something. But all of the various ways of complexifying it basically come down to this question of running all of these things we know down together. But then when we compare to real data, we find it looks persistently quite different. We can make it work at intermediate sized galaxies, usually something like a Milky Way sized galaxy, partially because we've calibrated the whole thing off of Milky Way-like galaxies. But we consistently and severely underpredict the abundance of bright and faint galaxies. Overpredict, yes. We observe fewer galaxies than we predict should be.
Underobserve.
Sorry?
We underobserve
We
though.
underobserve and overpredict, yes, saying it in the correct direction. Now, we have ideas, we have theories for why this is happening. We suspect that in the smallest galaxies with very weak potential wells, that supernovae go off inside the galaxy, and in doing so, they blast some of that cold gas back out and slow down star formation. And in the biggest galaxies, well, we know most galaxies have a supermassive black hole in the center. We know sometimes those supermassive black holes like to chow down on a bunch of gas and in the process drive big, hot jets of emission. And it's entirely reasonable that in doing so, they would do some combination of heat the gas so it can't form stars or blast the gas out of the galaxy. So we have some idea why these things are happening, but we can't remotely do something like this. We can't remotely parameterize supernova. We call these things feedback because they're ways that the activity of baryons inside the galaxy feed back on the baryons falling into the galaxy. We can't even begin to write down a physical parameterized model for, exactly how much we overpredict these things. We don't even entirely agree on the mechanism by which, say, AGN feedback slows down star formation activity. I said it could heat the gas, it could blast the gas out. There's, some evidence that there is a phase where a merger sets off a bunch of extra star formation and sets off the AGN at the same time. So maybe the AGN are actually positively correlated with star formation. And the more we look at galaxies, the more we recognize that this simple picture of cold baryons accreting down the cosmic web onto a halo is incomplete. And what we in fact have is a horrible, massively multi-scale problem where we have the megaparsec scale cosmic web. We have the large scale structure of the universe dominating the large scale gravitational dynamics, forming halos and having the cold baryons accrete down filaments. We have the galactic disk structure itself, which is kind of a kiloparsec to 100 kiloparsec scale object. We have the molecular clouds. This is me attempting to draw the Orion Nebula, which is not going to work, which are parsec scale structures on which the stars actually form. And then we have things like the supermassive black holes, or the supernovae, which are AU scale objects. And we can't do all this at once. This process, all of these processes are too complicated and nonlinear to write down a nice parameterized model to describe, let alone one that we could, hope to do Monte Carlos over. And you can't simultaneously, in a numerical simulation, simulate a large enough volume of the universe to accurately account for all of this stuff, while also resolving the small scale star formation and especially resolving that central supermassive black hole all at once. Even if you spend a ridiculous amount of time on it, you just can't handle all of that at once. I've heard this problem expressed by some of the hydra simulation people before as nature hates theorists, because everything is so horrifically coupled. So this is just a problem. So this reduces us to astronomer tools, astronomer questions about, back of the envelope estimates and scaling arguments and fine tuning and things that I'll talk about in a little bit. But there is no hope, basically, anybody has of writing down a lambda CDM-esque model that can describe all of this to anywhere near the level of precision that we're accustomed to with the galaxy surveys.
This is off topic, but I just want to say that this is true, I believe, in all of the physical sciences now. All theories are now mixes of numerical things at some set of scales and then bullshit all below,
Yeah,
I believe.
yeah. So one way of
Like the ocean, like the Earth models, it's
Yeah.
brutal because we really need to understand the Earth right now.
Yeah.
But they're also in this category.
So one way I might describe the difference between the cosmology and the galaxy evolution sciences is that you have to dig a lot deeper into the cosmology before you hit the bullshit levels. Whereas in the galaxies, they pop up right away. As soon as you try to do anything remarkably similar, you find yourself in a tangle of nonlinear, horrible physics. So why should we care about any of this? Especially if you're like a particle physicist in this room, question of why can't we just say, okay, this problem is hard, let's just go do something else. To steal a point from Hogg's Blackboard talk a couple weeks ago, there are basically two reasons to do astronomy. There is the origins argument, and there's the fundamental physics argument. Origins-wise, these are basically why you do astronomy. In Hogg's talk, you were talking about exoplanets. Exoplanets don't tell us much about fundamental physics, but obviously they're critically important for understanding the question of the origin of life in the universe. For galaxies, galaxies are a fundamental structural unit of the universe. And people originally referred to them as things like island universes. They're the stage on which all of the smaller scale, the formation of stars, the formation of planets, the possible existence of life, all of that plays out. And so if you're interested in the history of the universe and the origin of the universe as we see it today and our life, galaxies are a key step between kind of the large scale Big Bang theory, say, and all the way down to life. There's a lot of steps in here, but it's pretty inarguable, just like looking at pictures of the universe, that galaxies are an important step in this process. And from a fundamental physics perspective, we're starting to run into a lot of areas of research where problems like this are limiting our ability to study fundamental physics. In particular, there are a whole class of so-called small-scale dark matter anomalies in cosmology, where, for example, if you run an n-body solution, you predict that a galaxy like the Milky Way should have more satellite galaxies than we see. Or if you look at the density, predict the density distribution in the centers of galaxies, it looks different than what we see. And people get really excited about that because, for example, if dark matter, there are various ways in which dark matter could interact with itself or have a velocity dispersion that would predict exactly those results. But almost all of those anomalies can, at least in principle, also be explained by these kinds of nonlinear baryon effects. Maybe there are too few satellites because dark matter doesn't let few satellites form, or maybe there are too few satellites because a lot of them form their first generation of stars, then blow themselves apart with supernovae. Maybe the centers of galaxies look different because that's where dark matter density is highest and that's where interactions start to matter. Or maybe the density at the center looks different because there's giant constant explosions going off in the center of them, and that's going to move some mass around. And so even if you're a pure theoretical physicist, you just want to know about beyond the standard model, what is dark matter? There's a lot of directions where we're running into this wall, where galaxy evolution and galaxy feedback is kind of our fundamental limitation. And so there's a lot of motivation to push in, to push deeper, to try and understand some of these things, to try and understand these questions of galaxy evolution, to try and understand why the galaxy population looks the way it does, both to try and address the origins and fundamental physics arguments in astronomy. So this is kind of my introduction of why galaxies are hard and why should you care. What I'm planning to do for the rest is go through a more specific detailed model using the line intensity mapping data I work with and talk about some of the ways we are trying to take this problem and wrestle it more into that kind of shape. But before I start getting further into the weeds, I want to stop and ask if there's any other questions about this kind of whirlwind overview of a whole chapter of the decadal survey.
But so when you said that we kind of understand the reason why there is this discrepancy, you mean that just by with an order of magnitude that estimate it works, like this mechanism?
Yeah, we know these things happen, and you can kind of you can estimate the scale of the effect and show that it's about the right order of magnitude. But like for example,
I mean, yeah,
it's at least the right direction.
There's enough energy.
Yeah. But like, for example, you could easily imagine a world where like AGN feedback is slightly not efficient enough to totally cause this, and some of the remainder is caused by some weird dark matter interaction. And we would have no hope of answering that to a level of precision that would be useful. Okay?
So, but in cosmology, you kind of have the same, right? You have this tau for reionization that you don't really understand. So astronomer or cosmologists use these feedback parameters for AGN feedback and stellar feedback to marginalize over how strong these processes are.
Yep.
So why does that fail?
Yeah, basically because at some point those are the processes you're trying to understand. So like DESI, for example, DESI is measuring galaxies. So in principle, all of this physics comes into play on DESI's galaxies. But they're essentially able to do something like an effective theory where they can, because they don't care about this small scale physics, they only care about, honestly, scales even larger than these kind of baryon accretion scales. They can effectively integrate away all of this large scale physics and just treat every galaxy as a point source. All of this ultimately comes down, I think you would say, into something like the bias, the galaxy bias, and do something like CMB and marginalize over that. Whereas, supermassive black holes are a really very important part of the galaxies themselves. So if I'm trying to understand supermassive black holes, I can't integrate away the supermassive black hole.
That marginalizing over nuisance parameters works on large scales, but if you're trying to understand the galaxies themselves,
Yeah.
Or even medium scale structure, right?
Yeah, and even at some point, like I left out, for example, the fact that all these galaxies tend to have small satellite galaxies around them, which presents a notable problem when trying to do a DESI-like measurement on smaller scales than DESI did. Another way of putting it is you can marginalize all the reionization crap away into tau, but if you're trying to understand reionization, then that's a bad idea.
So, I mean, it sounds like a very difficult problem when you have to solve all these different scales of physics, and they're all coupling to each other and all these things. But maybe more naively, what if you just flip the question? So, if you understand the curves look like this, is there any way you can then, I don't know, say something interesting about, the behavior at these different scales? Can you use that to learn about if you understand?
I think that's more or less what I'm going to talk about we're trying to do now. More or less trying to do something in the middle where we don't marginalize out all the physics we care about, but we go from these measured things to infer something, at least. So, the reason why I got wrapped up in all of this stuff is that the thing I spend most of my time thinking about is this idea of line intensity mapping, which is kind of yet another data set for large-scale cosmology that has shown up relatively new in recent years. If you've been to one of my brown bags before, again, probably exactly the same in overview at various levels of details. But the basic idea is, just like in a galaxy survey, you map some large area of sky, but since we're not necessarily, if you're a cosmologist, you're not doing object-oriented astronomy, you think, well, for this measurement, I don't really care about the individual galaxies. I'm averaging out all the stuff going on in them anyway. So let's just make kind of a low resolution map instead of putting all the effort in to resolve the individual high redshift galaxies. And then because getting spectra are difficult, like getting a spectrum of each one of these galaxies to figure out its redshift and its line of sight distance, let's just pick a single emission line and make this low resolution map in a bunch of different frequencies. And since overly approximate definition of redshift that works for us, the emission frequency of a line divided by the observed frequency ties very tightly to the redshift, because that's how they're defined. By observing our line at low resolution in a bunch of closely spaced frequency channels, we can build up a three-dimensional picture of large-scale structure in a very similar manner to something like DESI does, but with fewer requirements on the aperture or the depth of the survey. And this idea is very attractive to the cosmologists, because basically we've already said that for most of these kinds of measurements, we don't care about the small scales. And so all we've basically done is taken our large scale structure map and low pass filtered it. And since the small scales that we're throwing away don't matter, we should in principle be able to do all of these things. But there's something else we've done to the map. We've taken every single one of these points and we've weighted it by how bright the galaxy is in this spectral line. So that means we're not just measuring the large scale structure, we're measuring the luminosity weighted large scale structure. And so if I write down a power spectrum of these things, which is the thing cosmologists like to write down, if you don't know what it is, it's not especially important. For a galaxy survey, this is a quantity where you Fourier transform the map and you basically compute the variance of the map as a function of spatial scales. But for a galaxy survey, what's important is that I have this quantity and the galaxies all track the dark matter. So my galaxy power spectrum looks like a dark matter power spectrum modulo some bias factor, which is what I said, where basically all of this crap integrates down into. But in the intensity mapping survey, I've taken all of that, I'll write it like this, I'll write it proportional. I've taken all of that and I've weighted it by the mean galaxy luminosity. And moreover, if you look at the Poisson statistics of the problem, you actually get a second component on here. That's the mean square galaxy luminosity. Now, for some purposes, the large scale structure arguments work fine. If I'm trying to measure the shape of the dark matter power spectrum, then at linear order, all I've done is added another constant in front of it. But the more detail I try to go, one, I start to run into these quantities as nuisance parameters. For example, one of the things people try to measure from galaxy surveys is effectively this AS parameter, this amplitude of the cosmological fluctuations. And I've basically made that entirely degenerate with the average line luminosity, which is some integral over this thing, which I don't understand. Question?
How do you measure the power spectrum of dark matter?
We don't measure the idea is we predict the power spectrum of dark matter from, on these scales, mostly linear perturbation theory. And then we measure the power spectra of the galaxies, and to way oversimplify, we say one is just a constant times the other, and just fit for that. But two, this means we have a bunch more information in our map that we weren't using before. And this has been especially useful because the surveys that are being built to do this technique are kind of brand new, like 10 to 30 person collaborations that do not have the level of funding or sensitivity or manpower to remotely be competitive in this 6 parameter space. But this is the mean luminosity over the entire population of galaxies that exists. That means that any of these galaxy surveys has a fundamental limit in that far away stuff is hard to see, so they will only be able to ever see sources above some luminosity threshold. Whereas these data will be able to see all of the galaxies that exist. So on paper, this is one of these things we love to find in astrophysics, where this is a new window, where we're potentially getting access to a whole population of sources that we can't see otherwise. And every time we do that in astronomy, we tend to find weird things that we don't understand. But understanding it requires not only doing all of this for an individual galaxy, it requires doing all of that for all of the galaxies and then integrating over it and then doing it for multiple different lines at the same time. And now we are back to, I really want to just do a Bayes law on my power spectrum, but I can't. Somebody raised a hand?
So I was just gonna ask, it feels like we're losing some line of sight information when we're integrating the luminosity, so it's nice that we're able to see farther, fainter stuff, but how do we resolve?
Yeah, so I've made the implicit assumption here that we're we're doing this over a narrow enough redshift range that these quantities aren't evolving with redshift, because in principle, like this is actually L of z squared B of z. Like in principle, all of these things about like star formation, history changes in redshift, and all of that fun stuff. So in this paper, we took one of the currently existing intensity mapping data points, and we tried to be, well, first the people who wrote it, made that measurement, tried to be cosmologists about it, and then we tried to be cosmologists about it slightly better. So we were looking at an experiment called MIME, which is the millimeter intensity mapping experiment, and glossing over a bunch of details for the purposes of the Blackboard talk, they basically made a measurement of this L squared term at a frequency, a wavelength of 3 millimeters, or a frequency of about 100 gigahertz. And so, if you didn't follow any of the numbers, any of the power spectrum crap here, the idea is I have a measurement that's purporting to give me some moment of a luminosity function at a specific frequency. And this frequency, there are several different emission lines that are contributing to that. They are primarily rotational transitions of the carbon monoxide molecule. So you have CO2 to 1 at redshift 1.3, 3 to 2 at redshift 2.5, 4 to 3 at redshift 3.6, and 5 to 4 at redshift 4.8. So we have this measurement. We know from line physics about which lines it's coming from. What in the hell can we say about anything based on that? So there are basically 3 different ways out there of trying to get a handle on galaxy results like this. The first one is to use scaling relations, empirical scaling relations. And this is that classic astronomer game of measuring 2 things and drawing a power law through them, and then saying, say, the slope and intercept of this power law are the parameters of my model. So for CO lines, the thing that is tended to do is carbon monoxide is a molecule. It shows up in places where molecules exist. So there is a standard scaling relation in astronomy where we say the amount of molecular phase gas in a galaxy is some constant times the CO10 luminosity of that galaxy. This is mostly an empirically derived quantity. And so what the authors of this MIME survey did is they took this measurement and they basically said my L squared observed is some constant times some theoretically predicted L squared. And then they compiled a bunch of scaling relations together to make a prediction, and then asked how much brighter or fainter do we need to make that prediction to match this data. And I don't need to go through the details of how they did it, except to say that doing so required guessing a broken power law form for the mass-luminosity relation, calibrating the luminosity ratio between these lines and the 1 to 0 line off of a sample of 3 galaxies at redshift 1.5, calibrating the CO10 to infrared luminosity from a sample of 300 galaxies at redshift 0, assuming a well-established linear-ish relationship between infrared luminosity and star formation rate, computing a star formation rate versus halo mass from a big abundance matching process that mixes a bunch of observations and a bunch of n-body and hydro simulations, and finally pulling an alpha CO from that same sample of redshift 3, of 3 galaxies at redshift 1.5. And in doing so, they eventually got to a point where they said, they measured, this is some integral over the luminosity function, therefore it's some integral over the amount of H2. So they measured the total amount of molecular gas in the universe, and they said it's consistent with pre-existing measurements. Which is another way of saying, I measured H2 from all of the galaxies, and I compared that from somebody's attempts to measure it from just the brightest galaxies. I got the same results, so everything is consistent.
Meaning, like, you take the bright galaxies, you do some extrapolation.
Exactly.
And that extrapolation is okay.
Exactly.
How do they deal with the fact that there's many different redshifts?
That's what a bunch of those that's what a bunch of those assumptions were for.
Okay.
We can talk about it a little bit offline.
All right.
Maybe, because I want to get to the end a little bit. But all of that stuff I just said has basically no physics content in it. And it involves mixing redshifts, high redshift, well, there's galaxies at redshift 1.5, galaxies at redshift 0, none of which are actually the redshifts of this survey. We know some of these quantities evolve with redshift. Just as an example, this relationship has to change with metallicity. It has to change with how much carbon and oxygen there is in your galaxies, right? If I'm at the very first generation of stars and there's no carbon yet, then it doesn't matter how much H2 I have, I'm not going to get any CO luminosity. And so this, this is an admirable effort. Like, I'm not saying they did anything wrong. This is just what this kind of analysis looks like. And when you compare it to the standards set by something like this, it's almost totally meaningless. There's like almost nothing you can really say about it beyond this is order of magnitude around the same as everything else. And just to show that, so this is one tool of trying to understand galaxies, this whole world of scaling relationships. The other tool, one other main tool is hydrosims, which I'm just going to not talk about because you basically can't do them for this purpose. This is where you try to simulate all of this multiscale physics from first principles. We can barely do it at the kind of order of magnitude level for individual galaxies, but we can't possibly do it for enough galaxies to simulate this entire galaxy population over this redshift range, let alone enough to start varying that, varying the parameters of the model and trying to fit even this one data point. There is an intermediate tool.
But just to get back, this number here, is that the number you're after? Is rho H2? Like,
So this
that's the
is,
thing you care about?
if you were trying to, an aspect of these scaling relationships is that the number you're after is almost forced on you by the scaling relationship.
Yeah, that's sort of why I'm asking.
So if this is the only law of physics effectively you're assuming to be true, then this is the initial thing you measure. You could also imagine measuring dn dmh2.
Sure.
With more detail. But this is a natural number to measure from the CO surveys.
Okay.
But you're basically taking a zoomed out measurement, integrated, where all the small scale physics is integrated out, making a bunch of empirical assumptions about the small scale physics from different sources, and then trying to back that out to a big integrated number, and that just doesn't work. There's an intermediate tool semi-analytic models, which you can think of as either, instead of using like zoomed out galaxy scale scaling relationships, using a bunch of smaller scale scaling relationships for individual components of the galaxy, or something like a numerical simulation with a really big grid. And these are kind of intermediate in that, unlike these, they at least try to have actual physics in them, and they try to predict multiple observables, but they try to be fast enough that you can run them lots and lots of times. And so this is the closest thing to like a real model, to like what a cosmologist would call a real model. But even Rachel Somerville, who's like a pioneer of these things, will tell you, we don't believe them to, you know, any particular high level of precision. And they still have tens of free parameters that you have to basically tune by hand. You can't, they're not done in a Bayesian model. It's still a hand-tuned model. And so to demonstrate even the limitations of the SAMs, we basically redid the same analysis, only we substituted that whole pile of empirical relationships for the ones derived from this particular simulation. And we found, at the end of the day, rho H2 that was quite a bit brighter than, quite a bit higher than the amount predicted by the theory. We found a few times more star formation in the universe. It ended up being, I think, about 3 sigma, which, you know, isn't very large, but it's suggestive.
What was the absolute difference?
I think it was about a factor of 10 in
Okay.
shot noise amplitude. So factor square root that
Okay.
in H2. But one, this whole thing where you just linearly scale all the galaxies, this should have a square on it, where you like linearly make all the galaxies brighter all at once. In doing so, because this is not a proper Bayesian calculation, will have broken all of the other things the SAM is calibrated off of. And this ultimate fit we're doing just of the amplitude, that still doesn't have any physics in it. So there are 2 other surveys.
Wait, can I just wait on this? Is the SAM calibrated at the appropriate redshifts and scales
It
for
is.
what's known, like meaning these scaling relations? Like,
It
because those are
depends.
things, those are
It
real
depends.
things.
Yeah, to some extent, yes. It's more, it has calibration at the redshift and for the lines we care about, but not nearly, it doesn't like integrate all the way down the luminosity function like these do.
Sure, I'm just asking like
Like
to get your rho H2, it has to do an extrapolation.
Yeah,
It's doing an extrapolation that's different than the scaling relation,
exactly.
but they overlap
Yes.
at certain, like
And
there's
they
certain
agree,
places where they overlap.
they calibrate off the data, they agree at the places where they overlap.
I see, okay.
But they're hand tuned to do that, they are
Yeah,
not.
yeah,
like
sure,
Monte Carlo
sure,
fit
yeah.
To do that.
That's all you can really ask of them.
Yeah, exactly. Yeah, that is.
If they didn't do that, then you wouldn't use it at all, I think.
Exactly. But I don't like that. And so there are other surveys, there are a pair of other intensity mapping measurements. COPS of a CO1 to 0 line and Planck of a C2 line of redshift 3 that are also quite a bit brighter than the SAM. But they're different lines in different redshifts. So we could do this procedure for all 3 of them, but it still wouldn't really tell us anything because all the information is still hiding in the SAM's abstraction of that multiscale crap. And more importantly, there are several different better surveys that are starting to or are going to have data that are going to go a lot further than just like a single integrated number of a single line. They're going to have multiple lines, they're going to be able to do both of these moments at minimum. We have tools where we think we can actually pull out the entire luminosity function of a line from these things. And this, even the SAMs are like completely not up to the task of trying to make any unified inference about galaxies from all of that. So with my last 5 minutes, I'm going to basically describe the goal of what we've been trying to do. And you can read this paper and the one I'm hoping to get out in the next few weeks to learn more about how we're planning to do it. So nobody thinks there's any world in which we can write down a unified parameterized model of all of this that anybody will trust. That's just, the physics is too nonlinear, it's too messy. That's just not a thing that's going to happen. But the more we look at this, and the more we think about this idea of, we have multiple experiments tracing multiple lines. We also, would love to be able to self-consistently model the intensity mapping data and the direct galaxy survey data. We think there might be a path to this other aspect that you get from the Lambda CDM cosmology, where if you pick a model, even if you don't particularly trust that model, you might be able to dump different types of observables into that model and see what they say in combination. Right? This way, the Lambda CDM models can take supernovae and galaxy surveys in the CMB and put them all together. And so, as I guess really just a teaser of what that looks like, the fundamental quantity we've decided to use as the specific thing we're trying to infer is what we have termed the conditional galaxy property distribution, where we take a set of physical properties of galaxies. For now, those are the star formation rate, the stellar mass, the H2 mass, the physical size, the radius of the galaxy, and the metallicity. And we say, what is the number, for halos of a given mass m and redshift z, what is the number density of galaxies that have these specific properties? And all that means in practice is basically you can run the SAM or you can run illustrious TNG, extract a bunch of galaxies from halos of a given mass and make another big corner plot. So as an example, we can look at one subset of this distribution, say, which two did I? Say stellar mass and star formation rate, which have a known correlation called the star formation main sequence. And we can say, measure this distribution from different simulations and see how they differ. But there's a couple of so the reasons why we do this thing, there's a couple of nice properties. One, as we explore in that paper, most scaling relationships people talk about, an awful lot of them, can be written as either some integrals over this distribution or some combination of this distribution and the model for a luminosity of a galaxy as a function of these parameters. Since these parameters are physical properties of galaxies, they're not like alpha CO, which is just some made up power law index. Basically, any simulation should be able to predict something like these. And basically, whatever physical model you use for luminosity should ultimately depend on something like these. This might not be an exhaustive list, but you can imagine that there would be a list that would determine all of these things. The other thing we found is that both for the SAM and TNG, which were the two simulations we tested, you can actually describe this thing to kind of 10% accuracy on all the individual scalings with a single component, well, I'm going to call it a single component Gaussian mixture model, but really with just a single component Gaussian. That means that for every mass, you can have five means and a covariance matrix, and a 5x5 covariance matrix that entirely describes this distribution. And that means that this then provides something that we can actually try to infer. So in the first paper, in the Zhang et al. Paper Yucheng wrote, we basically wrote down all the ways you can turn the tools astronomers like to use into integrals over this distribution and basically derived the fiducial values for these means and covariance matrices for the SAM and TNG. And then what I'm finishing up is an emulator to do the SAM, the Santa Cruz SAM's calculation of these line luminosities as a function of parameters. I think we're planning to make it publicly accessible. It's 1,000 times faster than the SAM, and you can run it on a laptop, which is great. And so the idea then is that as a function of these parameters, we can forward model both the intensity mapping observables, but also traditional galaxy survey observables, potentially using different values, different forms of this model, and take, in theory, you could do things as, extrapolant as compare like intensity mapping CO observations and JWST UV luminosity functions, if you emulated all those luminosities, and combine them all together in this one model space, and at least give you a language to talk about all of these different data in the same way. So at least import that one aspect of lambda CDM into this horribly messy world of galaxy evolution. So exactly how that inference is going to work is still very much an active area of research, but we basically have this forward modeling pipeline down, and we are actively working on applying it to data, and hopefully we will learn something cool from it once we do. That's where I'll stop.
Do we have more questions? I'm surprised it's one Gaussian, actually, at the high masses. Because like the star formation rate distribution, definitely like there's non-star forming galaxies, and
Important detail is we did only model the star forming, so we made a cut.
Got it.
We cut out the quenched galaxies
Okay.
for
Yes.
the purposes
Yeah,
of
then
this.
you're good.
Yeah, so in principle, I think you would, well, for most of the observables we're using, the quenched galaxies don't contribute anything.
Yeah.
Like
Yeah.
quenched galaxies don't emit any CO.
Yeah.
In practice, like if you were trying to measure like optical bands, luminosities in something, you might need a second set.
Yeah.
You'll probably start to need a second component.
Yeah.
We try adding a second component to just the star forming galaxies, and there are like tails on the distributions, mostly in the faint direction that it fits better, but we compute like all the various integrated quantities. It's like 10% accurate, and nobody believes any of these models to better than 10%, so single component is pretty good.
All right. Any other questions? All right, St. Patrick again. And there ought to be coffee and cookies waiting for us.
So, just gonna do
Okay, good.
There was one simulation suite that was used, so what was used to build up the conditional probability mapping these physical properties of those relationships.
Yeah, so at the moment we tested two different simulations. The illustrious next generation, which is a large, it's a good combination of large scale and good resolution hydro simulation,
Yes, makes sense.
and the semi-analytic models.
And the SAMs, right?
Basically because those are the two we felt had, we're basically making histograms to predict these distributions.
Right, yeah.
So
Okay,
we just
just
need
one
to
second.
simulate
Yep,
a bunch of halos.
got it. And
That's
like,
the best way we found to do that.
in like illustrious, so and it was these exact
It was
five.
those exact five, because the SAM model of this for the CO and CT lines, these are exactly the five that
Yeah,
go into it. Those are the five,
There
like,
may be food over there, and I can come meet you in a minute.
Yeah, I was just thinking about, yeah, so, cause I've been getting into the galaxy halo connections case, which is, this to say that at the most
Basically.
basic level, right?
Basically, yeah.
And so that's what I am building right now.
Yeah, this is along the lines of a galaxy, of a reframing of a galaxy
Yes, right,
halogen.
yeah.
Yes,
It's great, right?
the thing that like Peter and I want to do involves extending the relationship to more, I don't know what properties necessarily yet, but to more properties.
Yeah.
So like this to more physical galaxy properties is what our goal, our like next set of goals.
Okay.
So just being beside this
Okay,
and
great, we love that.
hoping that I can.
I'm at your service.
Yeah.
I need to fit better as well. I guess how, like illustration of these things are tuned to match some observational things today.
Right.
Right.
Mhm.
And the SAM
But
certainly
that's
are.
that's
Yes,
an
absolutely.
assumption that you put in,
No, let's
okay.
just go with it to some great sense, I
I
guess.
think this is a fair enough use assumption, except that I did not say that this unit has to be.
And so from your perspective, using those
Just to begin
as
with.
opposed to data directly is
Some kind of density, but
there,
if there
you
is
just
some
get-
kind of density,
well,
then
you're still matching the data, your thing is still built to match the data in
Yeah, well, so there's two directions. So right now, for the purposes of this paper, we're honestly, the main question we wanted to answer using the SAM and TNG things is basically, can we do like a Gaussian mixture model for them? Can we describe these distributions in some parameterized way? Because like, if this had some, horrendous non-Gaussian shape, then you couldn't do that. Okay, so we did find that, like, these are the actual like SAM distributions. But then the idea is that
Is it important that they are Gaussians? Like if you want, like,
it's not necessarily important. It's important that they're Gaussians if you want to model them with Gaussians. So the idea is that the Gaussian mixture model is we would basically none of us believe because it's all the hand-tuned, calibrated to some but not all, like whatever data they have in hand. The idea is that this is then the basis we would use for inference.
I guess it's plausible, but
So the
I
dream,
wouldn't say it's an
yes,
innocuous.
which we're not at yet,
I mean, I think
is you
several
dump
other people.
as much data as you
would
can
not
get your
call
hand
that
on
an
into a
innocuous
big.
assumption.
You forward model as many things as you
That there's
can
such
as a
limit.
function
It's
of
a
these
pretty
parameters.
changes
And then
the
dump all that
observations
into a big
dramatically.
Monte
Monte
Carlo.
Carlo and get these.
Yeah, exactly. And then you get some, you get some set of things that you then inferred from data. But in a like fully Bayesian sense,
Yes.
unlike the way the SAM and TNG.
Totally, yeah.
In practice right now, we have these things computed in bins of halo mass, which works just fine for a predictive model. But I mean, we have like 20 bins in halo mass at every redshift, and we have 5 means and 4, 5, 6, 7, 8, 10 covariance parameters in every bin. But fitting bin models like that is kind of dumb.
Fair enough, fair enough.
So we haven't figured
Okay,
out
you're still
exactly
saying
the best way
these
to
things,
do
I mean,
that.
that's fine, but you're still
Yes,
saying these objects form, right, so that's.
But yeah, the idea is
To get a
that
compelling story.
we
you
currently have
work
distributions on
say
disk that
how
are
they-
in some sense from the simulations that are calibrated
How
off
could
data.
you,
But we want
how would
to
they
be,
form in
we
the
want to
early
be more
universe?
cosmologist about it.
Right, yeah.
Patrick.
No problem. We
I
want
mean, you
to,
would form black holes and then evaporate.
we want to
down.
actually fit them.
Yeah.
Like I want to be able to say in a statistical, like
Yeah,
the CO and the C2 are brighter than the SAM predicts. I want to see, the dream would be to say, like in a statistical sense, is that because faint galaxies are brighter or are all galaxies brighter? Is that because there's more metallicity in low mass galaxies? Is that because there's more gas in low mass galaxies? Like right now, you can pick whatever scaling relationship you want to use and fit that,
Yeah.
but we want like the more like Bayesian posterior sense.
Yes,
Where we
and
can
so
say-
you just need a concrete model for which to have parameters in it. So
Exactly.
checking the simulations is what gave you this, like, okay, the Gaussian mixture bars is a concrete model that we, so
Yeah.
it's not arbitrary, otherwise how would you know
Yeah,
what to
exactly.
write down when you go to do the.
Yeah, we have a
actual
concrete
inference?
model that we know fits the simulations.
Right,
So
yes,
now
yes,
we
yes.
think we can in principle fit real data off of that model.
Because in cosmology, you do cosmology, you write down your metric, you go forward, and you come
Yeah.
up with, you add in your couple assumptions, you come up with a thing, so it's based on physics in that sense. Here, how do you do the equivalent? You're like, well, we'll look at the simulation,
Exactly.
and
some
Yes.
list of numbers like this has to be the thing that matters.
right, yes.
Yeah.
So you're also afraid that have you come to the right set of them, of course, but
Yeah, which nobody knows.
no
and
one
it's-
knows.
Yeah, so it's still gonna look more like galaxy astronomy, where it's gonna be a bunch of like even if like this worked as well as we dream it will,
Yes.
like it's still gonna look like trying a bunch of models and they all predict slightly different things, and
Yes.
then we argue about like, is that because of the feedback prescription, or
Yeah.
like it's still gonna look more like a galaxy science than a random
yes.
CDM, but at least
Yeah.
my biggest thing is I work on
But,
experiments with
you
different
can make
lines,
some observable.
and I want to be able to put both of them in the same possibility.
Yeah, yes, right, of course, that's what you want.
And I
Okay,
can't.
I'm gonna go get a coffee.
Like alpha CO is just alpha CO.
That's basically what got you started on this path, huh, was being like these maps are.
Yeah, like
For
these
specific
data, I
sets of
have
lines.
I have these multi-frequency data that, I'm getting more and more of them on my desk.
Yes, yes.
I would like to be able to do something more intelligent with.
How, and like you gave this list of CO from different redshifts. In practice, are there other less important lines that are contributing to this as well, but at smaller fractions? Like how messy are they in terms of the set of contributions?
It depends which line you're looking at. So this wasn't an intensity mapping talk, so I didn't go on this.
Yeah, yeah.
The CO 1 to 0 line there's this, they call it interloper lines.
Yes, interloper lines, that's right.
So it depends what frequency you observe at.
Yeah, sure.
The CO 1 to 0 experiments I briefly mentioned have basically no interloper lines
So it's one of the most pristine
that matter.
things.
These kind of mid-frequency range, you run into the CO ladder. Like CO is a diatomic molecule,
Yeah.
so like there's a thing in the back of Rybicki and Lightman where diatomic molecules have like a ladder
Okay.
of evenly
Oh, I
spaced
didn't expect
transitions.
that. Yeah, I
But,
see. For all the different diatomic modes, basically.
It's all rotational.
All rotational. That's why you're saying there's these different.
Yeah, so that's basically the J's. Did we stop recording this? I'm just gonna have to call.
Yeah.